Hello everyone, welcome back. So now we're in group problem solving 1. Uno. Let's see if we can do it. So what we have here is a free rolling ramp, and it's got a mass of 40 kilograms. We have a 10 kilogram crate that slides from rest at A down the ramp to P, and it's going to go off of that. And we're going to assume that the ramp is smooth, so no friction, and we're not going to worry about the mass of the wheels. Okay. With all that in mind, go forth and solve. This, however, is not a fun problem. it might seem simple, you're thinking there's got to be an easy way to do this. And sadly, it's not so easy. So, I'll give you that little caveat, so as I send you off to try it, you don't freak out if you can't figure it out. Okay? We can do it together afterwards. So with that being said, let's try it out. So 3, 2, 1, and you're back. Maybe you came back after a few years or a few semesters. If so, wow, that was a lot longer time pause than I was thinking. Otherwise, it was just a few minutes. It's good to have you back too. So, what's our plan? How are we going to do this? Well, we want to find the ramp's speed when the crate reaches B, and how we're going to do that? We're going to use our energy conservation equation, as well as the conservation of linear momentum. And the relative velocity equation. You're like, wait a second, relative velocity? Yes, it never goes away. None of these equations ever go away. You'll be using the very first class's equations all the way in the last class. So, here we go. Let's try it. So first off, we got to set up everything. So we're going to use conservation of linear momentum to begin. Now, we're going to have the velocity of the ramp. It's got a mass, and it's going to have some velocity moving backwards. And we also have the velocity in the x direction of this box and its mass. So for the x direction, we can see that the velocity of my crate is going to be equal to 4 times the velocity of my ramp, because it's 4 times the mass of it, or 4 times less mass. Then we pull out our relative velocity equation, because we need another way to connect these two. And so in doing that, we say, okay, well, this shouldn't be too terrible. And you look at it and you say, okay, VC, which is the velocity of the crate, is going to be equal to the velocity of the ramp plus my relative velocity. And I can break that all into components. Now the crate has a y and an x component. The ramp has just an x component. And relative velocity would be this. Now, with that, I can then solve for my velocity of the crate in the x direction, my velocity of the crate in the y direction. So I'm getting closer, If I look at it, I still got this third unknown here, and I don't know what VCY is. So I'm not quite to the point where I can solve. So we need to bring in another equation to be able to do this. But if we keep on plugging in, what we can get is that VCY is going to be equal to 8.660 VR. So I've got VCX in terms of the ramp, I've got VCY in terms of the ramp. So I'm getting there. So how am I going to solve this last little step? Well, energy conservation. Because while we can't figure out those components, we can find out the magnitude of my velocity by saying, well, all that potential energy that I had, that gravitational potential energy, has to go to kinetic energy. And it's not going to be just the kinetic energy of the crate either, it's also going to be kinetic energy of the ramp. So this gives me that third equation, because this is VCX squared plus VCY squared right there. And since we have both of those in terms of the ramp's velocity, we plug it all in. We can solve for the velocity of the ramp is going to be 0.601 meters per second, and the velocity of the crate would be 4 times that. Okay, so hopefully that makes sense. This is not a simple problem. We had to bring in a whole lot of equations. Our relative velocity equation, our conservation of linear momentum, and conservation of energy to be able to solve it. But with all of that, we were able to figure out the ramp's velocity. So never give up on these problems. Pull out conservation of momentum, pull out conservation of energy. Do whatever you think you need to do. If you bring all those equations out, because one of those tools or a combination will be able to help you solve the problems. So thank you for your attention. I apologize for the algebra this time. And I hope it helps you. See you next time. Bye-bye.